Okay, welcome back to asymptotics and perturbation methods. Today we're going to start a new part of the course on a technique that goes by the name of Wkb theory. And I've written out a lot of the lecture ahead of time because it's quite a bit of writing, and I just want to try to focus on the main ideas. There is one example at the end I want to do in some like real-time detail with you. A classic problem called the aging spring. And it's interesting. It has some good, slightly counterintuitive properties. So anyway, let me just jump in. Okay, here we go. Okay, so Wkb theory. This will take us maybe 3 or 4 lectures, after which I hope to get to this other topic of multiple scales, another powerful perturbative technique. But so Wkb theory, sorry about my voice. I don't know, I'm having some weird issue with it today. I just got my second COVID shot. I don't know that that's causing an unusual side effect that I should be reporting to the CDC. I feel pretty good otherwise, but sorry if my voice is a little bizarre. Anyway, all right. So W, K, and B are 3 mathematical physicists. That's Wentzel, Kramers, and Brillouin. And sometimes people add the name Jeffries to it, WKBJ. We saw earlier versions of this technique when we were talking about dominant balance as a way of solving linear differential equations. That trick being associated with the names Liouville and Green. So there are a lot of different, I don't know what you would call them, people who deserve credit for these ideas. If you want to read about it in Bender and Orsog, that would be chapter 10. It's a very standard topic. You can read about it in any perturbation theory book. All right, so let me first just make a few remarks about what this is good for and how it differs from what we've been doing so far with boundary layer theory. For one thing, Wkb theory is very much a method that's tailored to linear differential equations. So that's both a strength and a weakness. I mean, for linear problems, it really gives you some nice results, but it doesn't apply to nonlinear problems. So it comes in when you have the sort of situation we were dealing with in boundary layer theory, where there's a small parameter epsilon multiplying the highest derivative. So to that extent, very much like boundary layer theory. Now, actually, in this linear context, if we're just focusing on linear differential equations, Wkb theory, you could say, subsumes boundary layer theory as a special case. So I'll do an example showing that it actually gives you boundary layer theory. Just pops right out. So that's interesting. But the advantage that boundary layer theory has is that it can also work perfectly well on nonlinear problems, whereas Wkb, for reasons you'll see, doesn't apply in that case. So they each have their strengths and weaknesses. Wkb theory is really sort of ideal when you have a problem that has a global breakdown as opposed to a local breakdown in the solution as the small parameter goes towards 0. So you'll see what I mean when I do an illustration. But basically the notion is that instead of something going wrong in the neighborhood of a point, something weird will happen over the whole domain. And in that setting, Wkb can handle it, whereas boundary layer theory is kind of very focused on the idea of layers and more local issues. As far as where did this ever get invented and where do you use it, Wkb theory is a theory that comes up when you're dealing with linear waves, especially when they have some kind of slow modulation of their amplitude. In other words, there's like a fast oscillation and then an envelope that's varying slowly. That's, like in electrical engineering or communications, that'd be like the carrier and what's the other thing called? What's the envelope called? Like when you have amplitude modulation, right? You have this fast signal and then the slowly varying amplitude. So this comes up all over the place in quantum mechanics, in acoustics, any subject that deals with waves, optics. All right, so, okay, let us do a little example of the phenomenon of what I'm talking about with global breakdown. This is not Wkb theory yet. This is just a trivial example that you could, understand in your first calculus or differential equations course. Constant coefficients, epsilon y double prime plus y equals 0. In other words, it's a simple harmonic oscillator, right? I mean, just think of this epsilon as like the mass, and this is like a spring constant of 1. And so it's a simple harmonic oscillator if you think of the independent variable as being like time. And we'll give it some initial conditions. So suppose we started at, give it some boundary conditions. Y of 0 is 0, y of 1 is 1. So this is exactly solvable. And I just want to show you what I'm talking about what can go wrong as epsilon goes to 0. That's not a layer phenomenon, but something else. If you, just work out the exact solution for this, you'll get sine of x over square root of epsilon, then times this constant needed to make the boundary conditions work out. So sine of x over square root of epsilon means that these waves are oscillating with the frequency of 1 over square root of epsilon. I mean, if I think of it as omega being the term multiplying the x, like a frequency, right? That's going to infinity as epsilon goes to 0. So you're going to get faster and faster oscillations throughout the domain, but there's no boundary layer. So here's, I've just thrown in this little caveat. I mean, I don't want to divide by 0. So this term is not 0 down here, as long as I keep my epsilon away from n pi squared. But anyway, this is what the solutions look like. Here's a sine wave. And then as I lower epsilon, it just becomes a faster sine wave, right? Just starts oscillating more and more wildly. And as I say, it's not like there's a boundary layer. It's just that the solution gets more rapidly oscillating as epsilon goes to 0. And so Wkb is well suited to this kind of problem, whereas boundary layer theory doesn't really apply. Okay, so this is one kind of thing that can happen as epsilon goes to 0 in the highest derivative. Now, okay, what does this have to do with Wkb? So now I'm going to get into what the Wkb approximation really is. And so let me just write it down. I'm going to do a lot of algebra that's already pre-written because this is not super interesting. It's just tedious. But it's a very mechanical method. I mean, it's very systematic. You do the same thing every time. So here's the approximation. You're solving a linear problem. So you guess that y is something that depends exponentially on something else. You may remember earlier in the course, we had y equals e to the s as a standard guess when we were doing dominant balance problems to extract asymptotic behavior of, say, like the large x behavior of the Airy function or of Bessel's equations, solutions, that kind of thing. So we're doing something very similar. We're going to guess y equals e to something that looks like s, except now we have this parameter 1 over delta in it. So it's a little bit refined compared to the earlier y equals e to the s. And we also are going to expand this function s of s as a regular perturbation series in powers of delta. So function s of delta s1 plus delta squared s2. So there's regular perturbation theory being thrown inside this exponential, right? It's kind of combining a few different ideas we've had earlier in the course. The e to the s move is the one that goes with Liouville and Green. This little bit more refined thing with e to the 1 over delta s, and then expanding s this way, that's the Wkb ansatz or trick. Now, watch what happens. If I take that, well, first of all, I'm going to be applying this for today to second order ordinary differential equations. So I'm going to need to calculate both a first derivative and a second derivative of y. And so I want to just record them for posterity so that I can keep using them throughout the rest of the lecture. By the way, this quantity delta is going to depend on epsilon, and we'll determine it in any given problem by a dominant balance argument of the type we've used throughout the course. Actually, maybe before I wade into the algebra, let me see if you want to ask anything at this stage. Okay, nothing, we're good. So let's see how it goes. First of all, like I said, I just want to calculate some stuff, y prime. So we're not going to worry about the fact that you're not really necessarily allowed to differentiate an asymptotic relationship. We're just going to go ahead and do it and hope for the best. And if something bad happens, we'll realize that that might have been an erroneous move. But in practice, this step is fine. So I'm going to just differentiate both sides of this with respect to x. And so by the chain rule, well, I get an exponential of 1 over delta s, and then pull down a factor 1 over delta times s prime from the chain rule. Then I have to take this perturbation ansatz for s and substitute it in for s prime there and also for s in there. So you can see you're going to generate a lot of different terms with deltas in them. So if we do that, well, this is what we get for now. I'm just going to write down the first 3 terms and then dot, dot, dot for the rest of them. And that's good enough for now. Actually, you might wonder, by the way, why don't I expand out this term? Why am I not substituting for the s here? And the reason is that this exponential term is going to cancel out. Remember, we're dealing with a linear differential equation. Every term, y, y prime, y double prime, they're all going to have this exponential factor. So there's no point dealing with it because it's going to cancel out later. So I'll just leave it like that. It's really this term in brackets that's important. All right. So next, y double prime. Well, I have to differentiate the expression above. And I see that I haven't written my dot, dot, dot. Let me add that here. I should say plus dot, dot, dot. No, actually, maybe I'm okay. I guess what I did there was exact under the assumption in the ansatz, but I take it back. The dot, dot, dot comes in when I substitute for s itself. So let's do that. If I substitute for s itself, right, there are the dot, dot, dots I was worried about. Anyway, you get you can check that these are the different orders. The 1 over delta squared term, which we expect will be the biggest term because we're expecting delta to be something small. Typically, it will be of order epsilon. So this is going to be the dominant contribution. And then there's a 1 over delta term, which is also pretty big, has a coefficient like this. And then all this stuff is order 1 relative to delta. So all of that is obtained just by literally substituting my expression for s in here and collecting terms. So, okay, so I'm just going to record that for now. And we're going to use that, as I say, throughout the lecture. When I do various perturbation calculations and I look at order 1 or order, delta or whatever, we'll just read off some of these terms. Okay, so let me give you an example. A Schrodinger equation. So Bender and Orsag refer to anything that they use the term Schrodinger equation very liberally, not necessarily to mean the Schrodinger equation of quantum mechanics, but basically any second order linear ODE that looks like this. We've talked about this class of problems before. Epsilon y double prime plus a function of x times y prime plus another function of x times y equals 0. If this middle term is missing, okay, if that a is identically 0, that's what they call a Schrodinger equation. It looks like this. So it has a y double prime. It has a small coefficient in front of it, which for convenience, we're going to call epsilon squared rather than epsilon. It's going to turn out that epsilon appears most, it helps us avoid writing a lot of square roots later if we just predefine this thing to be epsilon squared rather than epsilon. The q of x is some function. And if you do happen to know some quantum mechanics, you might recognize that this term epsilon squared would be related to Planck's constant, right? That would be something like h bar squared over 2m. If the y is interpreted as the wave function in quantum theory, this would be epsilon would be proportional to Planck's constant, which is small in some sense. So whereas this q of x in the traditional Schrodinger equation would be related to the potential in the physical system. And also there'd be some eigenvalue, capital E, for an energy of the state. So we're not going to talk about the quantum example right now, just take this as a broad class of second order equations of interest, though, very close to the problem in quantum theory. Okay, so we want to try to write down an all-purpose solution for this, for y as a function of x, exploiting the fact that epsilon is small, and it'll be somehow in terms of this function q. Like you could, for instance, if the q were a constant, this looks a lot like something that has exponential solutions. Or if q were a negative constant, then this would be a simple harmonic oscillator and you'd have sine waves and cosine waves. So you sort of expect something that's going to be roughly sinusoidal. Let's suppose we're doing the negative case. It'd be sort of sinusoidal, except because this term depends on x, the frequency of the sine waves might change as we move around in x. That was the original picture. You're sort of thinking of a wave function that's oscillating fast, but then its frequency and its amplitude might change gradually as you move around in x, as you move through a potential well or some potential landscape or something like that. All right, so anyway, there's our setup. Now, we're going to assume, for reasons that you'll see in a minute, that the q is not zero anywhere in the domain. So assume q is non-zero. Later in the course, like 2 or 3 lectures from now, we will consider what happens when q is equal to 0 somewhere. And that turns out to be related to the interesting quantum phenomenon called tunneling, where particles can get out of a region that classically they would be confined to, like inside a potential well, and they don't have enough energy to get out. In quantum theory, they can tunnel through a brick wall with some small probability. And when that happens, you'll have a q that's 0, and you get an interesting thing where oscillatory solutions then decay exponentially outside the well. That'll bring in the idea of Airy functions. Anyway, that's all in the future. But anyway, so yeah, as I say, when q is 0 somewhere, the analysis becomes more difficult. We'll get to that later. So for now, q is 1 sine. All right, so what we want to do then to analyze this is we're going to substitute our Wkb ansatz in there for y and y double prime. So when I say Wkb implies this, I'm just reading off what I had earlier written down for y double prime. You'll recognize these various terms with their various powers of 1 over delta squared, 1 over delta, and an order 1. So all of this stuff is epsilon squared y double prime, except I've canceled out the exponential term on both sides. Over here, this should be q times y, but y is just that exponential. So the exponential has canceled on both sides, leaving us with this equation for our unknown function s, which looks pretty horrific, I admit, but remember, you're going to think about it perturbatively. That's the whole point. That you're not trying to solve for s exactly. You're trying to solve for s exploiting the smallness of epsilon. So what we do is try to look for a dominant balance here. And since q is assumed to be just some order 1 function, you can see that the dominant balance is when this coefficient, epsilon squared over delta squared, is order 1. That will get, if you do that, if you set this to 1, so delta squared equals epsilon squared, or in other words, choose delta equals epsilon. What good does that do you? That makes this term order 1, because this coefficient is 1. I'm sorry, I didn't say that right. This coefficient is 1. So the whole expression, we're assuming that S is varying in a way that S0 prime should be order 1 also. If we've chosen delta correctly, that will be the case. So anyway, this term will all be order 1. And then here, epsilon squared over delta will reduce to just epsilon, meaning that this is a small correction to this. And this is even smaller still. So we've now got a nice hierarchy of terms with this dominant balance. So all right, so putting in the delta equals epsilon, then you can read off the terms in this hierarchy. There's 3 of them. So at order 1, you have an equation where this term is being equated to this term, q of x. So that's what we've got right there. S0 prime squared is q. At the next order, this is the order epsilon term right here. We have to make this term be 0, because there's no order epsilon stuff on the right-hand side where q is. So you get 0 for that. And also this term, if we want to go to the next order, we're not really going to need this term, in fact. But if we wanted to, we could set this equal to 0 as well, and we could go to any order that we want. I mean, you can do Wkb theory to as many powers of epsilon as you feel like doing. What we're going to focus on is the lowest order approximation, which will be the order 1 and the order epsilon taken together. That'll be enough for our purpose today. So, okay, so now I have to solve all of that stuff. And you can read off that this order 1 equation is not too hard. You just have to take square root of it. And you get S0 prime is the square root of q. Actually, there's 2 roots, right? There's plus or minus the square root of q. Keep in mind, we're solving a second order ordinary differential equation. So you expect the solution to be a linear combination of two functions. So better have 2 solutions to everything that we do. So we get S0 prime is plus or minus square root of q. And we don't know anything about q other than that it's not 0. So we can't say much, but we can just formally integrate that to say S0 is the indefinite integral of the square root of q. And so for good hygiene, mathematically, I'm writing it as q of a different argument, q of t dt. You could say q of x dx. Nobody would be hurt by that, but you're not really supposed to. This is just a dummy variable of integration. It doesn't mean time. Call it whatever you want. But anyway, so we got some lower limit, which you can think of as some constant. I don't really know what a should be for now, but it's just it might be 0, it might be negative infinity, kind of depends on the problem. So some lower limit that's a constant, and then a running upper limit to this variable point x. That's our S0 as a function of x. Now that we have the S0, we can feed it into the equation at order epsilon, this one up here. Think of this as an equation for S1. So solving for S1 in terms of S0, you get this. And, well, I know what S0 is because I just wrote it down. So I can substitute for S0 prime in the denominator. That's this plus or minus square root of q. And likewise, I can take the derivative of that to get S0 double prime. And I'm going to try to keep my plus and minuses all straight. So I've written plus or minus here. And then when I take the derivative of that, I get plus or minus, but now 1/2 a square root of q in the denominator times q prime from the chain rule. And remember, the whole expression has a negative sign out in front that comes from this negative sign. So there it is. And what's interesting about that is that with all this configuration of or all these pluses and minuses, when this one is plus, this one is plus. And when this one is minus, this one is minus. So those end up canceling out to give you the same expression in both cases, minus 1/4 Q prime over Q for both of the solutions. And notice, by the way, that now we're really using the fact that Q is not 0, because otherwise we'd be potentially dividing by 0 at some point here in this denominator. So that's where I'm making use of Q not 0. Anyway, this whole expression, S1 prime is minus 1/4 Q prime over Q. You can integrate both sides of that then to get S1 is negative 1/4 log of Q plus a constant. So this 1/4 is a very famous thing in the Wkb method. You don't see too many 1/4s in physics. I mean, 1/2 comes up a lot. Obviously, pi comes up a lot, square root of 2. But this is the day in the sun for 1/4. I mean, if you ask me what part of math or physics do you associate with the number 1/4, I would absolutely say Wkb method. So there it is. Now, at this point, its significance is not clear, but you'll start to see that 1/4 is in it for the long haul, and it's going to be part of the story. All right, anyway, so let me combine the S0 and the S1 to give me my lowest order Wkb approximation. So it's y of x, also regarded as a function of epsilon, is exponential of s over delta, which now that we know delta is epsilon, this is S0 over epsilon plus S1 plus higher order stuff that we don't need for our purpose today. And then substituting what we just calculated, we get in this nice blue box the thing that people in physics refer to as the Wkb approximation, or the leading order term in the Wkb approximation. So let's see what's going on there. I mean, okay, we had the S1, maybe we should go slowly. I have exponential of a sum, right? So exponential of a sum, you do exponential of the first term times exponential of the second term times exponential of something of order epsilon, which would be of the form 1 plus epsilon plus higher, I mean, in other words, once I get to an order epsilon term in here, I know that I'm at the end of my order 1 calculation for the whole expression for y. I guess what I'm trying to say is, let me say that a little more explicitly. If I have e to the 1 plus order epsilon, no, I don't mean to say it like that. Let me say it better. If I have an e to the order epsilon, like e to the epsilon something, I don't know, f, that's 1 plus epsilon f plus ... So what I'm saying is that this term right here will contribute a 1 that multiplies these other terms and then times other stuff of higher order correction, which I'm not interested in for right now. So all that correction is going into this order epsilon term. But the other terms, e to the S0 over epsilon, that gives me stuff like these two right here. It's my linear combination of the two solutions. One that says exponential of the 1 over epsilon, here's my S0, that funny integral. And then here's with the negative sign, that's the other solution, that's my plus and minus, that has its own coefficient, C2. So you get basically a superposition of exponentials with this 1 over epsilon factor in them and this interesting modulated, this x dependence in here involving the square root of q. But then there's this interesting amplitude factor that involves q to the 1/4 power, the 1/4 I was making a big deal about. So that's a kind of mild dependence, but it's there. It's not a constant. It does depend on x, but only to a q of x to the 1/4 power. I call it mild because if the 1/4 were a 0, then it wouldn't depend on x at all, right? I mean, so to the extent that 1/4 is a small number, this is a kind of mild x dependence. But anyway, it's showing you something. So there it is. So that's the Wkb in general for the Schrodinger equation. But now I want to make, actually, maybe before I go to example 3, let me pause there. Further discussion about this? Okay, I mean, it's a textbook calculation. We'll be using this later in more interesting calculations, but we had to go through it once. Okay, so I'm going to continue then. Here's this interesting point that WKB can do, anything boundary layer can do on a linear problem, WKB can do, and you might even say, and can do better. So let me try to make that case. I don't really think it's better. It has one advantage that you'll see at the end. So let's try a little rinky-dink boundary layer problem of the type we often do as a case study. This problem, which is exactly solvable, we don't need perturbation theory, but let's just do it anyway. Epsilon y double prime plus y equals 0, with boundary conditions y equals 0 at 0 and y of 1 is 1. So that's the kind of thing we used to grind out in boundary layer theory. We could do that again. You can check if you want. The boundary layer theory using our techniques with inner and outer expansions and then constructing a composite solution, that would give us this uniformly valid composite solution. E to the 1 minus x minus e to the 1 minus x over epsilon plus higher order stuff that we won't bother with. So this has a boundary layer near x equals 0, as you can see from this term. Right, that x over epsilon is showing us that something's happening of thickness epsilon around x equals 0. And then there's this outer solution here. Okay, so anyway, we get this uniformly valid approximation if we did boundary layer theory. Now, let's see what WKB would do with this problem. If you approach it with WKB, then as always, you make the WKB ansatz, y goes like exponential of an unknown s over delta. Plug that in. Well, actually use the s as a regular perturbation in powers of delta. And then plug everything in, collect all the terms. So it's all that stuff we wrote down before. And this is what it would come out to be in this problem. After canceling out the exponentials, you're left with an epsilon times the coefficient of the second derivative, which we wrote down earlier. It's this term that I'm underlining. Then there is a coefficient of the first derivative term, which is going to be this. I'll just remind you, here's the equation. Maybe I should make it a little smaller so you can see everything all at once. Here's my equation. So the y double prime has given rise to this term times an exponential that's been canceled. The y has given rise to an exponential which has been canceled, leaving a factor of 1. And there's a 0 on the right-hand side. That's it. So there's my hierarchy of equations. I do dominant balance on it. In this case, the dominant balance is when this term balances this term. You can check that that's the right dominant balance. When the this term from the second derivative balances this term in the first derivative. If you do that, I mean, you can try it out. You'll see that gives you a delta equal to epsilon again. And everything else is smaller. It's all consistent if you make that approach. So, I mean, for instance, let's just see what happens with that approach. If I take delta equals epsilon, this coefficient will become order 1 over epsilon. And so would this. No, it doesn't. Sorry, there's an epsilon that cancels this. So those two terms cancel, forget that. But this term right here would be order 1 over epsilon. Right, those are both big. Those are big, and that's why the leading behavior is at order 1 over epsilon, at which you get this term with this term conspiring to add up to 0. So the order 1 over epsilon is the biggest contribution to the equation. Then there's a contribution at order 1, which you can get by taking this epsilon and canceling it with this delta equals epsilon, right? Those two cancel. So you get this stuff. We've already dealt with this term. But then we're left with this S1, which has no coefficient in front of it, S1 prime, and a 1. And those are the guys that are appearing here. Whereas these two terms are the ones appearing here with their delta having canceled with that epsilon. So you can see why I wanted to write this out ahead of time. It's easier to just draw with a laser than to have to write everything down. Anyway, so that's my order 1 equation. And then if I wanted to, I could do order epsilon, but I don't need it.
Do we always assume that the S terms are order 1?
Yeah.
In the interval?
Yeah. Yeah. That's what we're assuming.
Okay.
Yeah. The S terms are not depending on epsilon except through the perturbation ansatz. I mean, right? That's what, so it's a good point. What we mean when we write this is that the only dependence on the small parameter is through this kind of expression. So you can, you're doing it that's how the small parameter gets in there into the S, not in any other way. So yeah, so this S0 is truly meant to be of order 1. And this S1 is supposed to be of order 1. And this delta is supposed to reflect that the whole term is of order delta. There could be situations where this won't work, but this is the vanilla version of Wkb. And as we could see from our derivation, it does work, for this fairly broad class of Schrodinger equations. Although this problem we're doing now, of course, is not a Schrodinger equation because it has this y prime term in it. But anyway, good. Okay, yeah, good question. Is there another question? Okay, so let's now start solving. At order 1 over epsilon, we have this. So to solve that, I have 2 different equations I have to solve. I could either have S0 prime is 0, or I could have S0 prime is -1. So those are my 2 options, and I'm going to call them A and B. These 2 cases right here. There's the case A, there's case B. So in this case, S0 just becomes a constant, whereas in this case, S0 is -x plus a constant. So we got to keep those 2 cases in mind, and those 2 are going to give us my 2 linearly independent solutions that go into the general solution of this ODE. So anyway, there's case A, there's case B. Now we have to keep those 2 cases in mind when we go to the next order at order 1. So now I have to deal with that equation. And I can use, like, let's suppose I think about case A. I use this information, but now feed it into the order 1 equation. So that's going to be very nice, as you can see, because S0 being a constant means that this S0 prime term will disappear. This whole term will be gone. This second derivative term will be gone. And we're just left with, for case A, we just get 2 terms remaining. These 2, S1 prime plus 1 is 0. And then that can be instantly integrated to give S1 as -x plus a constant. Likewise, in case B, where we were here, S0 was -x plus a constant. Then when you look up here, thinking of S0 as -x plus a constant, here you would get a -1 term. Here we would get 0. So this -1 that's appearing here gives me 2 times -1 plus 1. That makes a -1 times S1 prime. Then plus this 1 equals 0. So solving that gives me S1 is +x plus a constant. Remember, this is now at the next order. This is the S1 equation. So putting everything together, what I get is that my y, which is supposed to be exponential of S0 over epsilon plus S1, feeding that in, and you just do each case one at a time. Actually, let's focus on case A. In case A, we have S0 is a constant and S1 is -x plus a constant. So when I put that stuff in here for S0 and S1, and keeping in mind that e to a constant makes a multiplicative constant for the whole expression. That's where this C1 is coming from. You might wonder, why did I not write C1 earlier? Why am I just saying const? Because I want to reserve C1 for this term right here. I don't want to start counting C1, C2, C3, C4. The only constants that matter are these at this stage. This multiplicative constant times the e to the minus x that comes from this S1 being negative x. So that's what case A boils down to. And then case B gives me this. There's one term. This comes from the S0 term, the negative x over epsilon. And this term, the x, with a positive sign, comes from here, from S1 in case B. How's it going? You're still with me on the algebra? Okay. All right, so you can see I've got some undetermined constants, and then I can impose my boundary conditions, which were y of 0 is 0 and y of 1 is 1. So the first boundary condition gives me this, C1 plus C2 is 0. The second boundary condition gives me this kind of ugly expression, C1 e to the minus 1 plus C2, and then this thing equals 1. But I want you to recognize that this whole term is a transcendentally small term. Because, right, you've got this minus 1 over epsilon. You're sort of taking e to the minus infinity. This is exponentially small, and we're only doing lowest order perturbation theory. There's no, these transcendentally small terms are baked into the whole calculation to begin with. I mean, we're only doing asymptotics here. We're making transcendentally small errors to begin with. Right? I mean, those are always lurking in asymptotic calculations. So there's no point keeping track of this. In other words, I just want to ignore this whole term for simplicity. And so I could, I suppose, drag it around and calculate C2 in terms of it, but there's no reason to. It's best to just delete it, and then you can solve easily for C1. It just becomes E. And C2 then from this equation becomes negative E. And so I'm left with this nice expression for my y of x, much cleaner than I would have gotten otherwise. And I'm making transcendentally small errors. I know what I'm doing. That's fine. So that's why I'm writing this as asymptotic. But one other remark for further cleaning is, let's look at this term. Think about this carefully. I mean, when is this term significant? Well, here's what I want to argue. That term is only significant in the boundary layer. Why do I say that? Suppose that this x term were order 1, like suppose it was 1, literally, right? Then what would happen? You'd have 1 over epsilon here. That would be completely dominant compared to 1 and x, because x is confined to the interval 0 to 1. So these terms are just order 1, whereas this term is order 1 over epsilon if x is order 1. So what I'm saying is this term will be completely dominant over these, and it will cause the whole term to be transcendentally small, exponentially small. So everywhere outside the boundary layer, this term is negligible. Whereas inside the boundary layer, well, then it's not negligible. Then x is of order epsilon, and you have to keep this term. But so what I'm trying to say is, now that we know the only place of interest is inside the boundary layer, that means that the x is going to be negligible compared to the 1. Right? Because now we're deciding that x is less than or equal to order epsilon. That's where we're paying attention. And so then we might as well ignore the x. So that based on this argument, you might as well write this whole term as e to the 1 minus x over epsilon. And that will give you a uniformly valid approximation. And what's interesting is that that's exactly what we got in boundary layer theory. We've just reproduced boundary layer theory, except when I said anything you can do, I can do better in Wkb, you'll notice that I did not have to do any matching. I never did asymptotic matching. I never did any overlap region or any of that stuff. It just popped out. The matching is just takes care of itself in Wkb theory. So that's a kind of remarkable thing. And that's what I'm talking about when I say that this is a global method as opposed to a local method. You never had to really think about the boundary layer. I mean, I guess in a way we did when we made these arguments up here, but these arguments were not essential. We could have ignored them. I mean, we could have just ignored this finesse and also this finesse. If we had just blindly carried out the algebra, we still would have gotten a uniformly valid approximation. It just would have been messier looking, and it wouldn't have been identical to what we got with boundary layer theory, but they would agree up to transcendentally small terms. So in effect, it would be the same thing. And we would have never done matching. So I find that pretty remarkable. And especially in problems where matching is tricky, like if you wanted to do higher order matching or something, WKB has an advantage in that respect. But as I say, its big disadvantage is that it's just for linear problems. Okay, so that was boundary layer theory recapitulated through WKB. Okay, so that's the end of that example. Is there any question about this example? All right, we're moving along pretty briskly. It helps if you write the lecture ahead of time. But I don't want to keep going at this speed because I realize it might be kind of boring to be looking at a lecture that's canned. But so I want to spend the rest of the time writing out the final example with you, which is a really nifty example that we're going to call the aging spring. So this example will come back later when we talk about the method of multiple scales. So it's a nice classic example. Actually, maybe I should not just call it the aging spring, but let me be a little more descriptive. I think I want to call it the slowly aging spring. Get over there, you demon. There. Okay, so that's our problem. Now, what is the slowly aging spring? Imagine a physical system. You've got a mass on a spring, and the spring is getting old. I mean, it gets weaker and weaker as time goes on. Maybe it's slowly disintegrating, or something's happening to it. So, but it's on a very long time scale. Might take, whatever, 10 years for it to kind of get, like that actually happens with rubber. You probably noticed that if you have rubber bands in your drawer for a long time, they get kind of dried out and nasty and lose their elasticity. So that's one kind of aging. But here I'm just going to model an aging spring in this way. I'm going to assume that its spring constant, its stiffness, decays to 0 exponentially, but exponentially slowly. So we'll write it this way. X double dot plus, so dots meaning time derivative, e to the minus epsilon t times x equals 0. That's my governing equation, where epsilon is very small. Okay, so that's like F equals ma, kind of, with this a linear spring, except that it's spring constant. It's not really a constant. So I guess I'm setting the mass equal to 1 if you want to think of it that way, or I've chosen time scales so that the coefficient of the x double dot is 1. But anyway, the spring stiffness, K, is actually a function of time. This exponentially decaying thing that starts out at 1, but then, very slowly decays. Okay, so I have this slowly decaying spring stiffness. And actually, you can see that when T is large enough, I mean, if T is very large, like much greater than 1 over epsilon, then, well, then we're sort of dealing with the equation x double dot is sort of like 0, which is, that would describe a particle that has no forces on it at all, right? That's just inertia. That's just a particle that's going to drift. Like you would expect at very, very long time, x of t might behave sort of like some constant. Think of it as some kind of velocity. I don't know. Not sure what notation to use here. Let's just say vt plus a constant. So it'll stop oscillating, in other words. So I'm just trying to build up a little intuition before we solve this problem with Wkb method. But so it should stop oscillating after a long time. But before that, when it has a spring, it should oscillate. And the time scale, for the decaying of the spring is this 1 over epsilon time scale, whereas this number is itself order 1. And so if you think of it, I mean, really, like if you're good with oscillators, you'll recognize that what I'm really saying is it's kind of like the natural frequency squared. I mean, sort of your intuition would be that the natural frequency would be kind of like this coefficient of x, right? So that would suggest that the frequency at any given time should be something like e to the minus epsilon t over 2. It's kind of an instantaneous frequency of oscillation. Angular frequency. So we expect that the oscillation should get slower and slower as time goes on, and eventually stop. All right, so those are a bunch of things we could say without knowing any perturbation theory. But now let's see what we can do with our technology. All right, so how are we going to approach this? I mean, here's our equation. You'll notice it does not, at the moment, look like any equation we've talked about. It doesn't have a small epsilon in front of the highest derivative. But we can get one there by changing the time scale. So if we consider what's happening on the slow time scale over which the spring deteriorates, we could say, let's let capital T be epsilon little t. This is what we're going to think of as the slow time. So it's slow time in the sense that, t is equal to 1 unit of slow time when t is equal to 1 over epsilon, which is a very long ordinary time. So that's sort of like measuring time in centuries or millennia or something like that, instead of in minutes or seconds. Okay, anyway, so in terms of this new variable, big T, what happens to our equation? So I'm going to think of x of t as some slow variable, some variable that depends on the slow time, big X of t. And then to transform derivatives, my original dx dt I can think of as d big X, d big T times d big T, d little t. And that brings in an epsilon. So you can think of this as, if this is x dot, this would be epsilon. I'll call it x prime. Prime will mean slow time derivative. Right, this term is what I'm calling x prime. Okay, so similarly, if I do x second derivative, that will be epsilon squared, x double prime. So my equation becomes x double dot now becomes epsilon squared, x double prime, plus the aging spring. So we have, it's just a function of epsilon t, so it's e to the minus capital T. So now it's looking very much like what we've been talking about throughout the lecture. I mean, in fact, this is a Schrodinger equation now. So it's a Schrodinger equation. Pardon my German. Actually, Schrodinger was Austrian. So I should say what? Schrodinger, something like that, maybe, roughly. Anyway, Schrodinger equation with a Q of T in our earlier notation. The Q, remember the Q is the factor of this term. This is the Q, except when it's on the right-hand side. So our Q of T would be negative e to the negative T. All right. So we could just go through the whole WKB again, but we already did it. So I don't see any real point to doing that. Let me just use our earlier results and just feed this stuff in there. Or maybe I'll show a little bit, since practice makes perfect. Oh, a Schrodinger equation. Yeah. So what would we do? WKB would say that we should try x of t asymptotic to exp of 1 over delta S0 plus delta S1 plus ... And so if you do all that, you'll find again that the dominant balance, as before, was delta is epsilon. And my equations come out to be, so skipping a bunch of steps, but you can easily reproduce them or just plug into what we derived earlier. You'll get at order 1, S0 prime all squared is plus e to the minus big T is 0. And let's just deal with that while we're here. That tells us that S0 prime is what? I have to take a square root of a negative number. That's interesting. So I'm going to get plus or minus I, and then the square root of e to the minus t gives me e to the minus t over 2 for my two roots. And so my S0, when I integrate, is going to be minus over plus 2i e to the minus t over 2. The reason I said minus over plus is to account for the behavior of this negative sign up here in the exponent, meaning that the plus of this one corresponds to the minus of the S0. So anyway, there's my S0. I could write plus constant, but I'm not going to need it. because that we all know how the constants are going to appear in the end anyway. So let me just circle this. This is my S0 as a function of time. And let's also now carry out what happens at the next order. So at order epsilon, the equation comes out to be 2 S1 prime S0 prime plus S0 double prime equals 0. Should look familiar. And when I substitute that in and solve for S1, substitute in for S0, you get that S1 prime is minus a half S0 double prime over S0 prime. Do the substitution, you get minus a half minus over plus I over 2 e to the minus t over 2. And then in the denominator, plus over minus I, it's an I here, e to the minus t over 2. And a whole lot of stuff cancels out, and it ends up just becoming 1/4. The famous 1/4. So that's very nice. I mean, we can instantly integrate that to get S1 of t, capital T is 1/4 t. So there's my S0, there's my S1. And so my overall solution is big X of t is asymptotic to C1 exponential of minus 2I over epsilon e to the minus t over 2. I'm feeding in the S0 stuff there. And then plus 1/4 t plus higher order stuff that I'm ignoring, plus C2 x, the same thing, except with a positive sign. Right, maybe I should just circle so you're clear that there's a negative sign here and a positive sign there. Those are my two solutions. Now, it's a little confusing, even for those of us who are professionals, to be looking at exponentials of imaginary arguments. It's a little more down to earth to use sines and cosines. So let's just do it that way. In terms of sines and cosines, oh, did I forget something? No, I'm good. Yeah, actually, let's stare at that. If I look at this carefully, I've got exponential of imaginary arguments. That's going to give me sines and cosines. But there's also a term, exponential of 1/4 t, which is interesting because that's what I earlier called the gradual variation, that square root of q to the 1/4. This is giving us a slow growth in amplitude that's actually exponentially growing. That did not see that coming, right? That x of t, according to this, is asymptotic to e to the t over 4 times, I'm going to, rather than use C1 and C2, which are going to have to be complex coefficients to give me a real solution for x. After all, this is a real vibration, so x is real. I can write it in terms of other constants in front of sines and cosines, like, let's call it A1 sine of this interesting time-dependent thing. What do I have to look at? I have to look at this, think of it as e to the I times some stuff. And the stuff is 2 over epsilon e to the minus t over 2. So that's going to be the argument of the sine function. It's this interesting object, 2 over epsilon e to the minus t over 2. That's how the time dependence comes in. Plus some other constant A2 cosine. Actually, maybe a little cleaner notation, whatever. Let me call them A and B, because I did this in Mathematica earlier and I called them A and B there. So I'm going to say A, B as my constants, cosine 2 e to the minus t over 2 over, I wrote that wrong. This is supposed to be epsilon. Plus order epsilon correction terms for the whole thing. So, you know, just notice this growing amplitude for one thing. So this is what Wkb is predicting for the behavior of the mass on this slowly aging spring. And to me, the notable things about it are that term, the slowly growing amplitude. Because remember that this big T is epsilon T. So if we want to write it in terms of the original time variables, it's saying that x of t is behaving like e to the epsilon t over 4, and then times a sine 2 e to the minus epsilon t over 2 all over epsilon, and then plus b cosine the same thing. Okay, so that deserves to be circled or put in a box where we can stare at it. All right, so now you might notice some interesting stuff like this term, the e to the minus epsilon t over 2. That epsilon t over 2 is reminiscent of earlier when we had talked about this frequency, right? We were seeing a frequency of e to the minus epsilon t over 2. So that's sort of an interesting coincidence, but it's not exactly what's happening here, is it? E to the minus epsilon t over 2. Well, it's pretty close. No, I guess it's still different, isn't it? Because if I were thinking of it as a frequency, it should be omega times t as the time dependence. Whereas here, it's not omega times t, it's just this thing. In fact, it suggests that the right time dependence for this problem is this whole compound argument. Like, it's sort of suggestive that the problem would be nicer suggests it's a good idea to define a new time variable, tau, that is this nonlinearly stretched time according to that formula, which I'm going to show you now is actually a magnificent idea. Wkb has hit upon something really clever that I don't think you could easily guess by just thinking. The Wkb has uncovered, in fact, the correct time dependence. If you do change variables to this tau, it turns out that the aging spring problem becomes exactly solvable in terms of Bessel functions. It transforms the aging spring problem to the Bessel equation. So let me now jump out of my notebook here and show you what I did in Mathematica that I think you'll find interesting. So stop sharing this screen. I'm Let me share a different screen. Okay. Maybe that's too big. How about like this? Is that still readable? Yeah, pretty good. You don't need it bigger. All right. So solve the ordinary differential equation numerically. Let me pick an epsilon moderately small, say 0.505. I solve it in Mathematica numerically and tell it to plot the result. And notice some interesting stuff. So by the way, I started it with x of 1 and initial velocity of 0. So it's like you take the thing, pull it back to unit amplitude, let it start oscillating. And what does it do? So notice it starts oscillating and its amplitude grows. That's the e to the t over 4 I talked about. I should probably draw e to the t over 4 or some envelope so you can see what it really is supposed to look like. But anyway, it is growing in amplitude and not just linearly. I mean, you can see it's curving up in amplitude. So it's growing, but then at long time, it stops oscillating and becomes linear. But we knew that would happen, right? At some point, the spring becomes so weak that the mass thinks it's free and just goes off drifting by inertia. So it oscillates for a while, then it does something else and goes off linear. Now, what does Wkb have to say about this? That was the numerical solution. So the Wkb solution I just wrote down, here it is, exponential exponential epsilon t over 2 a sine of that interesting argument plus b cosine of that interesting argument. And then I have to calculate the a and b to satisfy the initial conditions. So I told it to do that, and Mathematica returned these weird numbers for a and b. I plug them in, I get the Wkb solution, and now let's look at the plot. So Wkb is shown there in orange or whatever that color is that I never know in Mathematica, and blue is, no, I did that. Yeah, that's right. Blue is the numerical. Orange is the Wkb. So notice that Wkb is totally on top of the numerical solution and starts to show visible departure out here at time around, I don't know, 120 or something. So think about that. What do we expect? I mean, Wkb should work up to time of order 1 over epsilon. I had used an epsilon of 1/20th. So 1 over epsilon would be time 20, and it's working like a charm at time 20. And it even works pretty well out to time 40 and 60 and even out to 100. By time like 6 times 1 over epsilon, it's starting to screw up. Now, we shouldn't be too surprised. We're only taking leading order in the Wkb method. We could do higher order terms. We never did the epsilon squared term and, whatever. Even the epsilon term, right? Wait, did we? I guess we only did the first 2 terms is what I'm trying to say. So if we wanted to get better accuracy, you can just take more terms and it will work longer. But anyway, it's interesting that it doesn't know about the straight line behavior. It starts to curve in a way that's not right. Still, it's not terrible out here, but it's not really right either. But so here's the thing that I find very interesting, that you can solve the problem exactly. If you just ask Mathematica to solve it, it can solve it. It's a very simple little equation. Still, it's a pretty messy looking expression involving the Bessel function J0 and also the Bessel function Y1. But the thing you got to focus on is what's the time dependence. So I'm trying to blow up my screen. Let me blow it up a little bit. Excuse me for 1 second. If I make that 300, maybe you can really read it. See the time dependence? It's the Bessel function of the argument 2 times, that's a square root of e to the minus epsilon t. That's e to the negative epsilon t over 2 over epsilon. It's finding the correct time dependence. Wkb knew what would work exactly. And so And that's the only time dependence that appears in all these terms. So anyway, it's cool that even though the method is only approximate, it has hit upon the correct time dependence. And if you change to that time dependence, the problem becomes a Wentzel equation, which is why it's even possible to solve it exactly in the first place. Okay, so that's all I'm going to do today for the WKB method, but next time we'll put it through its paces on some more complicated problems. And gradually we have to return to what happens if our Q doesn't have one sign. And we can go from exponential behavior to oscillatory behavior. So that's coming, I think maybe 1 or 2 lectures from now. Okay, I will see you then.